presentation today will be about keeping the Blink clients up to date, and in the context of long polling in an Akka cluster. I myself, as you mentioned, a senior backend developer at Blink. And a few words about ourselves, as the company that sponsors me to be here. So we are an app for front-end workers. Our main goal is to give them the tools, removing any friction from their lives and get them as productive and as engaged in the company that they work for, as this has in the past been a problem for companies which deal with a lot of front-end workers. They have suffered from a lot of turnover. They have suffered from staff not being engaged enough. We try to eliminate that. And for the past couple of years, we have managed to get a lot of traction in that area, and we are currently growing exceptionally fast. So yes, do check us out if you're interested in that particular topic. So the problem we are facing, or we have been facing, is keeping all those clients up to date. So we're obviously dealing with both the frontline workers and the office workers. So we have to keep both the mobile devices and the potential desktop devices up to date. The requirements we have had to deal with are obviously three: reliability. As we are dealing with frontline workers, people who move around, they can move to underground, for example, when there is no network coverage. They can move to buildings, switch between networks. This poses significant challenges to the reliability of the connection they are having from their mobile device to the backend. Also, we have to deal with the people who support them from the comfort of their office. So those people can be behind proxies, that can be behind enterprise firewalls. This introduces further problems to the choice of the solution that we will use to keep the clients up to date. We have to be compatible because we are working within the context of an enterprise environment where you still deal with technologies which are quite old, if you think about a very quickly changing IT environment. So we often deal with old Internet Explorer versions from the browser environment, or we deal with old devices for the frontline people who some of them may have phones that are 10 plus year old. And finally, us, when we started being a relatively small team, we needed the technology to be easy to use, as we were aiming to deliver a big change in the environment rather than spend a year of building our network stack to be reliable. So what are the potential candidates in this space? First of all, we got active polling. That's an age-old solution where the client actively polls the server, just performing a request response to the actual server on a timer and sleeps in between. The good things about it is it's just HTTP request, HTTP response. It works. That's how the internet is built on. That's what the internet is built on. The bad problems with that is latency. Obviously, you can only update when the client actively asks for the data. And it's a resource hog because constantly creating a request response model between the client and the server is the expensive part in the interaction. And you cannot win in this system in that it's a zero-sum game. If you improve one, you lose on the other. If you improve latency, you have more connections, you utilize more resources. The first thing that came around to improve that model was long polling. And the way it changes the model is that it introduces a way for the server to continue keeping the connection open until it actually has something to return to the client. And in this model, obviously keeping the connection open is far cheaper than reestablishing the connection constantly. We have a better latency because the connection is there waiting for any notifications to be delivered, and we utilize less resources, like I mentioned. The bad thing, obviously, is the potential for message loss, as we are dealing with people who can constantly move in and out of network coverage. There's a potential for message loss where the connection is going to be interrupted at the same time as the delivery started. And the client will reestablish a new connection, new polling connection, where it will receive a new packet of data without actually receiving the previous one. It's potentially resource intensive. That may happen in a situation where your system has a lot of active notifications going through, and the client and server end up constantly polling for very little data. So your client polls for data, receives one notification, gets a response, polls again, one or two notifications, response. Very, very high utilization, very little benefit. And finally, you may need sticky sessions, what is called sticky sessions, depending on how you implemented your backend. If you keep the state of the client or subscriptions for the client in a single place, you may need to introduce a system under which your connections end up on a single machine. So in this case, you give up on any kind of load balancing, and you potentially expose yourself to security issues with regards to denial of service, because if you give someone an ability to target a single machine directly, that can be used to deny that machine any service. The next solution is the one probably most of you have heard about. That's the one most people just think about instantly when they think about keeping the clients up to date. That's WebSockets. That's already a well-established solution as well. It works by establishing a persistent channel, bi-directional channel between the client and the server, by utilizing an upgrade protocol embedded in HTTP. Now, the good things about it is obviously it's extremely fast, low latency, lightweight, bi-directional. However, because the protocol was effectively added as a bonus to the specification, it was added in a very raw form, and it requires additional development time or use of libraries to provide resilience. So the protocol itself just provides you with a channel. It doesn't give you any handshakes, doesn't give you any recovery mechanism when the connection gets broken, any missed content, missed packets, no such thing. So it's also prone to compatibility issues. So like old browsers do not work well with it. I think Internet Explorer, for example, only supported WebSockets from version 10. And while this may be old world for us, it's not for a lot of companies still. There's also problems with proxies and VPNs. And most importantly for us as well is there's a problem with enterprise firewalls. Many enterprise companies just outright ban them. They do not allow WebSockets. Going through the process of enabling them is often painful and long. So they would stop adoption. And at the end of the day, if you use a library, many of them fall back to polling anyway. So you might end up implementing two solutions to one problem. Finally, the newest arrival to this problem is called server-side events. And the way it works is it utilizes the HTTP request response, as most of those solutions do. However, it does something smart. It doesn't provide content length. It doesn't specify content length, and it just continues responding as long as it can, effectively providing a single channel that sends responses to the client for as long as it can. And that would be ideal because, again, it's a standard model that the internet is built on. It handles all the issues that WebSockets do not, because it's been with the knowledge of what WebSockets kind of were bad at. So all the things about disconnects, missed messages, and all those kind of things were built into the spec. However, because it utilizes the HTTP request and response model, there is a problem where the very built-in caching that's part of the internet may literally kill off your communication mechanism, because an old proxy that's not aware of the mechanism may completely buffer your stream and effectively stop any communication you have between yourself and the client. Likewise, it's not supported by a lot of old browsers, including pretty much every version of Internet Explorer, meaning it cannot be a solution for any enterprise that still relies on that browser. So finally, we arrive at the game of elimination. We effectively have 4 solutions, and we had to figure out which one we can go ahead with. Active polling, absolutely not acceptable, too resource intensive, too many problems. WebSocket, likewise, while it's very fast, it's prone to a lot of network issues. It requires quite a lot of development time or using libraries. The problem with libraries is, depending on how many platforms you need to deploy to, you may be lucky and the library will support all those platforms, or you may not, and you end up in a situation where you have a library that doesn't work with a particular platform you need to deploy to. And like I mentioned before, most of them require an implementation of polling anyway. The newest one, server-side events, no IE support basically means we cannot work with it in terms of enterprise clients. So we're left with long polling. There's still load balancing issues, there's still message loss ordering, and there's still resource usage under heavy activity. The question is, can we build the system in such a way that we can deal with those drawbacks? And that's where we can utilize technology. That's where we can utilize some of the frameworks that are available to us. So the first thing we use a framework called Akka. Many of you may have heard about it, but I'm going to do a small introduction. It's a framework that models system behaviors or behaviors in your system in general as small single-threaded state machines called actors. It's a highly asynchronous model and it's a highly parallel model. However, at the same time, it's a very programmer-friendly model in that you effectively deal with a single-threaded processing within the context of the actor. The actor has a mailbox which you can send commands to, and the processing is in order. So the first message that arrives is the first message that gets processed. However, however, the most important feature for us is that those actors are addressable, which means any actor within the system can send messages to any actor within the system as long as it knows the address of that actor. Now, there are two additional features in Akka that made a big difference for us, and that is clustering, which means we can have multiple boxes servicing our system, servicing our core servers that can talk to each other. They can assume different roles. They're resilient to network changes. They're resilient to nodes going up and down. And at the same time, we do not have to think where within the context of the entire system the actor lives in. As long as we know the address of the actor, we can target it. It also provides us with a very efficient binary comms protocol, which is far more efficient than HTTP in terms of distributing change throughout the system. There's also a cluster pub subsystem, which allows us to subscribe actors, which are going to be our termination points for our long polling, to various topics of interest within the system. The system has a very low footprint, as per node, there's only one actor that actually tracks the topic, and a memory footprint of 250 and 512 bytes. And there's only one message propagated per topic per node, as the actual fan out happens in memory. Another very important feature for long polling in this case, and for the entire system, is that you can perform topic subscriptions anywhere within the system on any node, because the topic subscriptions get propagated using the gossip protocol. So the cluster nodes tell each other which actors are interested in what topics, which nodes are interested in which topics. So you can subscribe an actor on one node from another one. So how can we utilize all that tech that I've been talking about to address the three core weaknesses of long polling? First of all, load balancing. The clients establish a polling session, which is terminated on an HTTP server. However, it's represented by an actor. The actor is stateful, it's addressable. That means that the client, if it receives a polling identifier, an actor address, it can then hit any of the machines, any web server, and that can be directed within the cluster to the actual polling actor. So we can utilize load balancing for HTTP connections because we no longer have to think about which server box are we hitting. It also means that the clients can utilize that address because of the gossip protocol to, for example, when fetching any resources, immediately subscribe to those resources again on any of the machines within the cluster. So that's one weakness addressed. The second problem is clients start the message loss and ordering. So we can utilize, again, the statefulness of actors to deal with that, because we can have two buffers, a delivered buffer and a current buffer, with, for example, an auto-incrementing index. And a client can provide us with the information of which of the two it requires. If it successfully got the previous batch, it will ask for the next one. If it didn't, it can ask for a replay of the previous batch. That can be stored in memory, it can be compressed, or it can be stored in a cache system like Redis. If it asks for the new batch, then we just discard of the old cache and we complete the current batch, move it to the deliverable one, and we deliver it. Very, very simple solution because of the statefulness of Akka to get over the message loss and ordering of the responses on the client side. And finally, the last problem with long polling, very well known, is that if we have a lot of activity in the system, long polling suffers because it constantly delivers very small batches of information at a cost of creating and discarding connection. And what we noticed is that in our case, those events tend to be aggregated. So when we deliver, when one of those events arrives via PubSub, many will very soon follow. As they get triggered by the same mechanisms. Usually, one event results in a couple of those notifications. That allows us to utilize the statefulness of actors and the ability for them to effectively turn into a state machine. Because what we can do is we can transform the actor from the waiting state to a delivery state. For example, when there is a polling connection present, when there's something to deliver, we can then delay that delivery for a period of 200, 300, 500 milliseconds, while we aggregate any kind of notifications that still arrive and then deliver them to the client as a single batch. And ideally, hopefully, and in our cases, in most situations, by the time the client requests another polling session, basically we've delivered the entire payload. So we do not pay for this high activity in the system. And that's pretty much it. That is how we can utilize Akka. That's how we can utilize the system design within the Akka cluster to get rid of the three most painful and largest problems with long polling.